Hey everybody, Dr. A here, and in this video we're going to be exploring another example of statically indeterminate torque-loaded shafts. So let's go ahead and get started. Given to us, we're being told that a shaft is made from a steel tube which is bonded to a brass core. And we're being asked to compute the torque reactions in each of those materials at the fixed end. So what we want to compute is the torque reaction in the steel tube and the other torque reaction in the brass core. The diameter of the brass core is 1 inch and the outer diameter of the entire tube is 2 inches. We're also given that the shear modulus of steel is 11,500 KSI and the shear modulus of the brass is 5,200 KSI. So the figure that we're given here shows this steel tube. That's what we see here in black. And then we have this brass core, which is represented in red here, this red hatching, okay? The entire length of the shaft is 6 feet, and we see the fixed connection is back here. And then at the free end, we have this applied torque moment of 200 pound-feet, okay? So to go ahead and get started, why don't we start with computing the section properties that we need for each of these materials. So if you recall, we're going to end up needing the polar moment of inertia values for both the steel tube and the brass core, okay? So let's say that J of the brass, okay, that's the core, right? That's this center solid cylindrical shape is going to be equal to pi d to the fourth over 32. Now, what is this d here? Well, that's the diameter of the brass core, right? And so we're going to say that that's pi times 1 inch raised to the fourth power over 32. So if we get out our TI-36X Pro calculators, really that just becomes pi over 32. And so we get 0.09817 inches to the fourth power, okay? Now let's go ahead and get the polar moment of inertia of the steel tube, all right? So the steel tube is an annulus, right? It's a ring. So because it's a ring, we're going to say that that's pi over 32 multiplied by the outer diameter of the entire shape to the fourth power minus the inner diameter to the fourth power, okay? Now, if you are a little rusty or you don't remember these formulas of polar moment of inertia off the top of your head, you want to look back at some reference material. You can find these formulas either in an FE reference handbook or in a mechanics of materials or even statics textbook. So we're going to say this equals pi over 32. And we know that that outer diameter, we were told, is 2 inches. So we're going to say 2 inches raised to the fourth power minus that inner diameter, which is 1 inch raised to the fourth power, okay? And so let's punch this through in our calculators. 2 raised to the fourth power minus 1 inch raised to the fourth power, which is just 16 minus 1 is 15, times pi over 32. And for this moment of inertia, this polar moment of inertia, we get 1.473 inches to the fourth power, okay? And we're going to use these values here in a few minutes later in the problem, okay? The next thing we can do is we can write our one equilibrium equation. So remember, this is a type of indeterminate system because we have two materials that are bonded together and they're acting in composite. So whenever you have a situation like that, you still just have one applicable equilibrium equation. That's the sum of the torques equals 0. So you need an extra piece of information, which we call a compatibility relationship. So let's go ahead and start with the one equilibrium equation that we have available to us. So I'm going to use this original figure as my free body diagram. And in doing so, I'm going to go ahead and I am going to draw these two different reactions here. We have a reaction force here that is going to be called T steel. So that's the torque reaction developed in the steel material. And then we also have this torque reaction in the brass. I'm going to draw a little line here and call this T brass. All right, so think about it this way. You have this bonded material between brass and steel, and then at the free end, you have this applied torque moment that's twisting this composite cylinder. And so what's happening is the steel tube is going to handle or absorb a portion of the applied load, and then the brass core is going to absorb or withstand another portion of that applied torque moment. So those are the two reactions in each of the materials that we're looking for. So when we apply our equilibrium equation, so I'm going to write here equilibrium equation, what we're going to say is sum of the torques along the longitudinal axis equals 0, okay? And when I do that, I'm going to say 200 pound-feet, and then I'm going to say minus T steel minus T brass equals 0. Now, how do I know what the signs should be here? I made the 200 positive, and then T steel and T brass both have negative signs. Well, those signs, the plus and the minus signs there, are based on the directions of the 200 pound-feet and T steel and T brass. And remember, T steel and T brass right now are unknown, so I'm assuming their directions. And so I just arbitrarily assumed that they are rotating in the opposite sense of the applied torque moment, which I would say is a pretty safe assumption since they will be resisting that one applied torque moment. So that's our first equilibrium. That's our first equation, which is an equilibrium equation. Okay. Now, what about our compatibility equation? I'm going to write compat equation. All right. How do we set this up? Well, our compatibility equation is going to be based on the fact that each of these two materials, the tube and the core, are going to twist together, okay? So because they are two materials that are bonded and they are twisting together, each of their angles of twist will be equal to one another. So we're going to be able to say that phi steel is going to be equal to phi brass, okay? Now, we have a single segment of this composite shaft, right? Which means that we just need to use the most basic version of angle of twist. So I'm going to ask you this, and maybe pause the video if you want to answer it to yourself. I want you to recall, what is the formula for angle of twist? Pause the video if you want to think about it yourself before I give you the answer, because I'm about to tell you. So the formula for angle of twist is TL over JG, okay? So for the steel tube, we're going to say T steel times, let me spell steel correctly, T steel times L steel over J steel, G steel. And then that equals the same formula, but for the brass. So that's going to equal T brass times L brass over J brass times G brass. Okay. Now, recall that both of these materials have the same length, right? So we know T steel equals, I'm sorry, not T steel, L steel equals L brass, all right? And so because these lengths of each of the materials are the same, they're equal to one another, we can clearly cancel the L value out, okay? So they're both 6 feet, right? So we can say equals 6 feet. So 6 feet on each side of that equation cancels out. So what do we do next? Well, now we're ready to substitute our known values in. So I'm going to say T steel divided by J steel times G steel. So J steel we calculated a few minutes ago. That's the 1.473 inches to the fourth. And then G steel was given to us here as 11,500 KSI. 11,500 KSI, okay? And we're going to say that that's equal to T brass divided by J brass, which from earlier was the 0.09817, 0.09817 inches to the fourth, multiplied by G brass, which is 5,200 KSI, okay? And so what we can do is we can solve for one of these torque moments in terms of the other, all right? So I'm just going to go ahead and solve for T steel in terms of T brass. So all I'm going to do is kind of lump all those constants together. 1.473 times 11,500, and then that's divided by 0.09817, also divided by 5,200, okay? And so we get T steel is equal to 33.18 times T brass. And now what we can do is substitute this 33.18 T brass into the term for T steel in our equilibrium equation, and then we can knock out one of those unknowns and solve for T brass directly. Now here's where you got to be really careful, okay? Don't get too excited yet. What you have to be very careful with is your units. So if you notice, J has units of inches to the fourth, and G has units of kips per square inch. Looking back at our equilibrium equation, that 200, that was the applied torque moment, what are the units of that 200? Well, that's 200 pound-feet, okay? 200 pound-feet. So we got to be really careful here and be cognizant of what our units are going to come out to be. Now, the question at this point is, do we need to convert anything right now? So pause the video if you want to answer that question for yourself, because I'm about to tell you the answer. The answer is no, we don't have to convert anything right now. And the reason why is if you look back at our compatibility equation, you have this J term that has inches to the fourth on both sides of this equation. So the inches to the fourth cancels. You also have KSI on both sides of that equation, which cancel with each other now. So this 33.18 is a unitless constant. So you have to be cognizant of these units, but you don't necessarily have to convert anything right now because this relationship from our compatibility equation, the coefficient 33.18 is not carrying any units, okay? So anyway, let's substitute that into our equilibrium equation. We're going to have 200 pound-feet, and we're going to say minus 33.18 T brass minus T brass equals 0. And then we can do some rearranging and solve for T brass. And when we do that, let's see what we get. We're going to move the 200 to the other side of the equation, and then we're going to divide that by 34.18. And you see the negatives take care of themselves, so it becomes a positive. The 34.18 comes from saying 33.18 combined with this one coefficient here. And you should end up getting 5.85 pound-feet, okay? So that's T brass. What about T steel? Well, T steel, of course, is going to be computed as 33.18 times T brass. So you just take that 5.85 and you multiply by 33.18, and you should get 194.15 pound-feet, okay? And these are your answers. So let's discuss this for a second. Number one, does it make sense that T steel is significantly bigger than T brass? Physically, does it make sense? We just showed mathematically that it does make sense, but physically, does it make sense? Well, yeah, sure. Brass is a much softer material than steel, okay? So it does make sense physically that the softer material or the weaker material is only able to support a much smaller fraction of the applied load compared to the harder or the stronger material being steel. So from that perspective, it makes sense, okay? We also need to account for the fact that it's not just about the material property, in this case G, that's influencing how that applied torque moment is being sustained by each of these materials. It's also how much material you have, right? So for steel, you have a lot more material than you do for brass, and that's reflected by the polar moment of inertia, okay? So in summary, it does make sense that the steel tube is supporting a much, much larger portion of that 200 pound-feet than the brass core is. And the last observation we want to make is that, of course, as you can expect, if you added these two together, T brass plus T steel, what do you get? Well, you get 200 pound-feet, which is equal to the magnitude of the applied load, which again makes sense. So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other material like this. Thanks for watching.